So we have a panel. This is the last agenda item before the reception. We have pretty good speakers, experts in their fields from different companies and the university as well. The theme of the panel is context and content-aware encoding for OTT. And we will get different opinions from the speakers. And I believe each one will have a set of introduction slides. And we want this panel to be as interactive as possible. So feel free to ask questions anytime. And we would like to be also fair among the speakers in terms of time. So since you have the microphone, let's start from there. Yep.
Good afternoon, and I would like to thank Alex for arranging this amazing conference, take this opportunity. So my name is Ilan Kaftan. I'm heading solution and technical sales at Beamer. Background, VP R&D at Harmonic, VP product management at Aries, Alcatel-Lucent. So many years of experience since the MPEG-2, since the mid-90s.
Perfect, thank you. Yuriy?
Hi, my name is Yuriy Reznik. I'm with Brightcove, and previously I was with a few wireless companies, Qualcomm, InterDigital. In 90s, I was with Real Networks, Real Audio, Real Video were my babies, so to speak. Before I did research, I was visiting scholar at Stanford, published a bunch of things, which most of them is garbage. But in any case, it's good to be here. And Alex, thanks a lot for organizing this.
Thank you. Kumar?
Thanks for inviting Ali. My name is Kumar. I'm the founder and CEO of Media Melon, a company in San Francisco. My background is a combination of technology and finance, and I worked at Lucent in strategy at IBM, and then I was an investment banker at UBS Warburg.
Perfect. Stefan?
Hello, my name is Stefan Lederer. I'm CEO and co-founder of Bitmovin. So Bitmovin is basically a product of the MPEG- standardization. We were 3 people, basically, also Christian Timmerer and Christopher Müller, working around MPEG- back in 2010. And based off that, MPEG- got, well, not based off that, but based off the community effort, MPEG- got a success. And also Bitmovin involved as a company out of that back in 2013. And nowadays we are more than 50 people in 7 locations worldwide. And yeah, I think try to get to the next level of quality on the web, which we will hopefully cover in this talk now, in this panel.
Thank you. Zhou?
I have been working on image and video quality assessment, structural similarity, and many other things for many years. And I'm currently still a professor at University of Waterloo. So we have a lab working on all kinds of image and video quality assessment, quality of experience assessment. And at the same time, we also have this company called SimWave. I'm currently the chief science officer of SimWave. So we are trying to deliver the industry with the best tool to do quality of experience measurement and optimization.
So I was based in London, Ontario for several years, and Waterloo is not really that far. And for those who are working in this field, I'm sure you have used SSIM at some point in your research or in your toolbox. Yeah, definitely. Thanks. All right, so who would like to go first with some slides? All right. Yeah, where's HDMI? There you go. Well, I hope it's not gonna. All right, perfect. Thank you.
So as I mentioned before, I'm from Beamer. Beamer is a company that's doing content adaptive bitrate products for codec 265 as well as for 264. I will cover the content adaptive and what does it mean, how can actually we leverage that, and what would be the outcome of using that. So the main question is ABR really adaptive? I mean, certainly it's worked well for a network. It was designed to actually accommodate and handle network issues and congestion, but it's really working with a fixed bitrate. So when we're actually doing the encoding, some call it all the rendition, some call it the ladder, ABR stack, we decide on a specific recipe for each one of the resolution, and based on the network condition, the client knows which one to use, which one to ask. But it doesn't really accommodate or adapt to the actually bitrate, to the content itself. Take the best encoder, doesn't matter which one, and you always leave bits on the table, what we call the either over-allocation or inflated bits, where you actually use too many bits while you can actually use less, or under-allocation, when you cannot actually exceed or get enough bits to get the right quality. Again, because you define a specific bitrate, 5 megabit per second, 3 mega, and so on. So how do we adapt the content to actually be more adaptive to the condition of the network and better quality, or actually allocate better the bits for each one of the resolution? So there are different techniques today to do content adaptive. We know that for talking heads or animation, you need less bits than you need for sport. But if I define a specific recipe, I will actually use too many bits for the talking heads or the animation, and maybe too few bits for the sports. So there are different techniques today. I'm sure that you heard on some of them. The basic one is, of course, doing it manually. It's very simple. It's actually very useful, but it's very slow. You cannot do it for a lot of content. You actually need to sit in front of the TV and tweak the setting, and actually for every content has its own recipe. That's certainly not scale, and not for production. You can do it by category. So you know that animation, actually Netflix start moving there, even with the VMAF. They realize it's for animation, you need actually less bits. So they said, okay, for all the titles of animation, instead of 5 megabit per second, I would use 4 megabit per second. While for sport, I would use 5 megabit per second. It's simple, but still, it's, you need to look at the content. It's not something that can scale. You need to do quality control, and for each one of the titles, actually to look at the category and the title within the category, still do some fine-tuning. And then you have the title base, and then you go for every title and you actually try to optimize the recipe for the title. We know that every movie, actually, to get the same quality, you need different bitrate. Again, you need for that, and VMAP actually doing that. You need a lot of CPU. It is very complex, and you cannot actually handle the changes or the differences between scenes. And then you have the frame content adaptive. So what does it mean, frame? So think about that you actually have a reference frame, which is the qualities that you like, and then using a perceptual matrix, you actually using different recipe that actually taking the bits out of the table. Meaning that instead of 5 megabit per second, I may go down to 4 megabit per second, 3 megabit per second. While I'm doing that, I'm keeping this perceptually identical quality. Very important to understand. Perceptually identical quality, it means that it's like simulate the human eye. So we know that the human eye, and we'll explain it later, is actually see different area on the screen and give priority to each one of them, meaning that for some area I may not be sensitive to, just a very basic example, high frequencies, eye is less sensitive than low frequencies. Details, if you have grass on a baseball game, its eye is very sensitive. You certainly don't want it to be soft. So assuming that I can actually do that, looking on a frame that I know that it's a good quality, and frame by frame, I'm using different recipe, and actually reduce the bitrate whenever I can, as long as perceptually they are identical. Sorry, guys. Yeah, sorry. However, in order to do that, you need to actually maintain 4 important things. It needs to be reliable, meaning very correlated to the human eye. I'm sure you heard about MOS, which is a mean opinion score, which is a subjective, but actually it's much more accurate than SSIM or PSNR. I don't have a few examples here. We don't have enough time, but certainly approach me later. I can show you a few examples where SSIM or PSNR give different scores, sometimes good, for some things that you can actually see the differences, or sometimes give very high score where the eye actually not see that it's actually not good, or low, or low score where they're actually very similar. So it needs to be reliable, it needs to be suitable. As we know, both HVC and AGVC are block-based encoding. And block-based encoding is very typical artifacts, edges, rings. So you need to correlate or make sure that your technology is very well correlated and suitable for block-based encoding. Adaptable, it needs to actually detect the specific features of the area, we'll see it later. And it needs to be low complexity, because you want to do it on production, you want to do it automatically, you want to do it on Oreo content, whether it's live or file-based, meaning VOD. In order to understand, here are a few different, these are actually adapting the quality to different areas of the frame. I mean, without going into detail, certainly because of IP, immediately you can see that on every frame, there are different tiles, and the eye is sensitive differently to each one of the tiles. I mean, when I'm sitting here, when I'm here and talking, you certainly look at me and you look less on these guys. So certainly, it's very important that I keep the quality of myself rather than the background. So when we do that automatically, we need to make sure that after using the different setting, the score of the new encoded frame is very close, very high to actually the original frame. Okay, the original frame is the targeted bitrate or the qualities that you would like to see. These are some examples that you can see the saving, and again, CABR is content adaptive bitrate. So you can see different bitrate, different resolution. The encoded was done with X264, by far the best encoder today. You use it in slow or very slow, I'm sure you won't be, no one of the competitors that you probably know could beat the X264. Maybe in performance, yes, but certainly not in quality. So we encoded those trailer and different clips with X264 slow, and although it's very good quality, running the optimizer as a second step, we've been able to save quite significant percents. You can see that animation, you have the most significant saving. This is why Netflix using different or more aggressive setting for animation. But it's very smart to look and say, okay, we can save bits, but how can I figure out on every content that I get what will be the saving? I cannot know it ahead of time. Therefore, it's very important to run it as an automatically. It's not smart to come back to me and say, you know what, okay, we saved 60%, so now I'm going to encode 60% less this specific title. Yes, you probably will get the same quality, but this is not something that scale because you don't know. You cannot actually go and change the recipe for every title. So these are some examples. You can see that the higher saving are on the 1080, and the reason is better the quality, better the saving. However, you can still see that we got nice saving on even 180. So what does it mean? You don't need a plug-in. I'm sure you are familiar with the VBR, cap VBR, some call it CRF, and CBR. Those are the modes that every encoder can use, CBR, VBR, or cap VBR. So what if you actually have a new rate control mode called content adaptive bitrate? Same codec, exactly as the previous one, but you get less bitrate. So what you see here is a linear graph. So the x-axis is actually the target bitrate, the qualities that I'm happy with. For example, I want for 1080, for 4K, 30 frames per second, use 18 megabit per second. I like this quality. And this is what you get. You define 18 megabit per second, you get 18 megabit per second. It's a VBR. It could be a little bit higher, it could be lower at any given point, any given frame, but the average is 18. But when you actually run it in a CABR mode, you get the same quality. As you can see, still the X, but the bit rate is much lower. So this is the nice thing about that. You actually take an existing workflow and just actually replace the codec, and actually you get a better saving. What does it mean? You will stay longer in high resolution. So yes, ABR helps you when you have a congestion, but whenever you go down on the stack, you actually sacrifice quality. But with the CABR, you can actually stay longer for better, with better quality, better resolution, high resolution. So that example for HDR, 4K HDR, and this is for 1080. Even here you see saving. Again, the same concept, target bitrate, qualities that I like is the x-axis, and the y is actually for the linear, for whenever you run VBR, it's the orange, the blue is actually the CABR. So the key takeaways that I want you to get from this short session is that ABR is important, but it's actually handle only network condition. It doesn't handle the content. There are a few techniques to do content adaptive, but most of them, with the exception of frame, are not scale, even though it seems to be simple. They are certainly not scale and doesn't really cover the scene change that you have in every content, whether it's animation or sport. And today with the generated graphic, you actually get a movie and actually animation on the top of that. So the only way to get a reliable solution is a frame-based content adaptive. It's really save the bits, keep the perceptual quality identical, and actually there are no really bitrate or quality trade-off. You get exactly what you want, just lower bitrate. The Beamer CABR, we have two products, Optimizer, which is a second stage for AVC, where you already have encoded content, and then we actually have a AGVC codec, we call it 5X, that actually we added the rate control on the top of the VBR. The results are excellent. More important, you don't really need any plug-in. It's a fully standard 264 or 265. Thank you.
Any burning questions? Yes, sir.
Are you looking just at individual frames and re-encoding those, or are you correlating between frames as well?
You have to correlate because so first it's done frame by frame, and yes, you encode it. But as you know, whenever I encode a new frame, it actually creates some different thing on the next frame, temporal flow. I'm sure you know that. So you need to take that into account. You cannot just say, regardless to the other frame, just compare one frame and say, okay, can you do a different setting? No, that's not work. You need to look on, the temporal flow and many other things. More questions? Yes.
For transporting, if there is the same resolution, even after transported, it's very easy to compare the PSMR. But if the different resolution, then do you have any idea to compare those?
So the technique is actually maintain the same resolution, the same GOP structure. So if you want to do it on 1080, you either encode it in 1080, just instead of VBR, you encode it with CABR. If you already have encoded 1080, then you just get 1080 on the output. PSNR, as I said, PSNR is it's a good technique. You can automate it, but it's not the most accurate. What we created is much more accurate techniques than SSIM and PSNR. And you know, again, if you come later, I can show you frames where PSNR can be great, but you will see immediately that the original and the optimized are not good. Or I can show you two frames, original, as well as the optimized, look identical, and PSNR is very low. So PSNR is a good technique and people using it, but I wouldn't say that it's the most accurate. More questions?
Yes.
Yes.
Can we integrate the algorithm with encode itself before encoding the string?
Sorry, can you?
Can we integrate the algorithm before encoding frame in the encoder itself, not after encoding itself?
It's come with the codec. So it's either a standalone solution, or for the 265, it's integrated. So you just use this codec and you get good codec as well as the optimizer. Yes?
I have a question.
Oh, sorry.
So how your solution is different from CRF?
CRF, I'll tell you, CRF even on CRF, we showed saving. The problem with CRF, and those that are not familiar with CRF is actually kept VBR. So there are CBR where you actually use 5 megabits per second, and VBR, the average bitrate is 5 megabits per second. But CRF is actually, you don't use all the bitrate. So yes, you get CRF, if you do it like kept at 5 megabits per second, then yes, you will have probably lower bitrate. What is the problem with CRF? The problem with CRF that sometimes you do need the bits, but you won't get the bits. So CRF will actually can create time or issues where you actually degrade the quality. If you actually use the VBR with the CABR mode, you get the quality but lower bitrate. So sometimes we will get and we'll show that we have the same CRF doing good in terms of saving bit, but the quality is not there. But we actually have many examples where we took content which is already encoded with CRF, and you still can save bits. And the reason is that rate control with all the tools that is 265, and the 265 has very nice tools, but it's mathematical tools. It's not really, it's DCT, it's looking on motion vectors, it has more tiles, more macro blocks, but it doesn't really simulate the human eye. And this is why it's subjective. Even today, ITU 500 is the most accurate to actually say this good quality or not good quality. Have I answered your question?
Also, in other words, what you're saying that you have better CRF.
You call it whatever you want, but as I said, we call it content adaptive bitrate because it's important to mention that the quality is better than the CRF in some cases.
Well, thanks. Well, we are going to hold on to the question because we really need to give time to the other speakers as well. Yuriy, please go ahead.
Okay, I think I'm going to have good questions too. So, Ali, thank you very much. This time my presentation goes to screen much faster. So I would be talking about both content and context-aware encoding, but I will focus actually on context-aware encoding more. And now, how do I switch slides? Okay, it works. So you've seen the slide before, just brief introduction. When we deal with ABR streaming, we need to encode to multiple bit rates. And the question arises, at which bit rates, at which resolutions you encode content? That's the key question. And of course, you could adapt it on a segment basis or a more fine-grained level, but just point is that at certain interval, at certain chunk length, you need to know which rates and resolutions to assign to content. Now, when I will be talking about what we are doing, we need to keep in mind that our context is different. Brightcove operates as the largest so-called online video platform. It's called Video Cloud. It's a publishing platform where content owners dropping us content and everything else, including selection of CDN, transcoding, maxing, and as well as video players are managed by our company. And that includes also collection of data back from video players and presenting them in terms of sorted analytics, where we know things like network statistics, usage statistics, impressions, and can help our customers to monetize and improve experience when publishing the content. So it's a kind of closed loop system. And what's interesting is that when we design profile generator in this context, this profile generator knows not only content that is coming for encoding, it also knows the context. For example, is coming from operator X, and we know that his population of viewers is distributed a certain way. He has certain percentage of viewers on iPhones, on Androids, and their network statistics look in a particular way. So in our case, we actually are aware of context, delivery context, and it is actually changing from device to device, from vendor to vendor, from region to region. And those changes are actually quite dramatic. And that accounting for these changes allows us to achieve better efficiency. Now, going to kind of encoding ladders, I show a few examples of static encoding ladders. The picture on the left is actually the latest Apple HLS authoring specification. It produces a ladder of about 8 resolutions, and it says which bitrates to assign for H.264 and HEVC codecs, respectively. It also says which frame rates to use. Other systems, such as our Video Cloud, if it uses legacy static profiles, it has more fine-grained tabulation when we assign not only specific bit rates, but also tolerances in terms of the VBRness of each bit stream, and keyframe frequencies and other constraints. Now, why static is bad? Well, there are two aspects to this. Of course, content is different, and the picture on the left is actually credit goes to Netflix. They had a blog called Title Encoding, where they just ran over 200 sequences and measured their RD curves. And this is PSNR versus bit rates. And you could see that some content is very easy. It goes straight to high PSNR numbers at very low bit rates, and some content is super challenging. You could throw like 50 megabits on this, and it's still about 30 dB PSNR. So, and of course, if you have this broad variety of statistic of content, picking single bitrate is not going to work. It's going to be an overshoot for some content, and it's going to be super horribly slow for small, insufficient for the other one. Now, the other aspect is this is variation of network statistics, and the picture on the left is on the right is actually from our Video Cloud analytics. It shows difference in PDF of networks when delivering to different class of devices. And you could see that, for example, Android devices versus iPhones have quite different statistics. Of course, TVs have much bigger bit rates, connected TVs. Tablets are somewhere in the middle. And this all changes based on region, based on content provider, and based on his audience. So to summarize and to put things in clear notation, we will use techniques that exploit properties of content to improve encoding as content-aware encoding, and techniques that use properties of delivery context as a context-aware encoding. And we will focus mostly on context-aware. In this work, also exploiting properties of content will naturally come in as a part of it. So now I said that I wrote a bunch of papers, most of them useless. So I'll try to be very brief here. And but this is kind of a very basic way to look at the problem of context-aware encoding. So on the right, I'm showing the probability distribution of network, and for simplicity, it looks like Gaussian. On the left, it's a quality-rate relation, which looks like sigmoid between very low quality to very high quality. In the middle is the effect of picking several points, in this case, 3 rate points, and the ladder that appears there is basically approximation of that sigmoid that will be realizable as clients will be switching from one rate to another. Of course, this model is limited to conditions that client is memoryless. It always picks the best rate possible given network conditions. In practice, of course, clients are also guessing which that rate is, and there is extra variation from this model. But the point to make is that if we know network distribution and we know the rates that are picked for encoding, we also know probabilities at which each of those encodings will be picked by the client during streaming session. And that probability gives us what? It gives us a way to express what would be the average quality experienced by users as they're pulling content from that network with those different probabilities assigned to each stream. And if we know how to express average quality, we can also pose a problem. How to design, how to pick those rates such that quality is the best possible given the network probabilities and giving rate quality characteristic of this curve. So that in a nutshell, and by the way, this is a variation on a theme of quantization problem where random variable is actually network bandwidth. So we just need to quantize network bandwidth to endpoints and such that our distortion, which in which case a quality metric is maximum. Now, this is an example of what it boils down to if we pick 5 sequences. For just simplicity of experiment, we will stick to same resolution, but we'll use SSM, and here are the rate quality curves produced by those, for these 5 sequences. There is ultra easy sequence to encode, there is also difficult sequence to encode, and there are a few sequences in between. On the right is also assumed network model. It looks like a wireless model, by the way. And basically, by using this optimization process, we could generate ladders. The optimality exists because you're balancing between how frequently the people will see a video with probability X and what the quality at that rate will be. And as you could see, the optimization process produces completely different ladders for different content, which is natural. And if we change network model, the ladders also become different. And what's also interesting is that for easy content, we naturally need fewer points to reach high quality. We're reaching, for example, for easy content, 0.97 SSM, just at 3 or 4 ladder points, and for difficult sequence, we never reach that point. It's 0.91 or something. You need probably 20 or 50 points to get there. So that's just a sense of where we are. And this is another kind of argument to say that not only we can pose the problem formally, we can also have an argument for how many ladder points is sufficient. And there are 2 arguments here. One is, if we look at the maximum point that we produced in this ladder design and say, well, let's assume that SSM 0.99 is good enough. And once you reach that point, you know that that's enough. You can stop at that number of points. The other is, well, if we increase number of points to infinity, we're eventually going to reach some optimal quality that is ultimately achievable given the network and characteristic of the content. And so the questions then become how far away you are from this optimality. And if you, for example, like 3 or 4% away from this optimal regime, maybe that's good enough. So practically, it doesn't make sense to go anywhere beyond this. So that gives a second criteria. And basically, the plots here shows that for easy content, we're going to very quickly find a maximum, very quickly reach the point of maximum quality and can stop there. For difficult content, we might never get a good quality, but if we know that you not even get quality of 0.95 SSM on this content, if ultimately you will be able to get 0.93 and it's just 3% away, maybe that's a good enough point to stop there. So That's another argument here and nice result. But of course, this is just a theoretical exercise, and in practice, it's much more complicated. And we've spent over a year working on this, and we actually have systems that incorporates lots of other constraints and conditions, and it is that practical. It is actually available right now on the market. So what we account for is multiple devices, different video resolutions, multiple networks, usage statistics. It's all pulled from Video Cloud, publisher preferences. Publishers could specify particular constraints for profiles, difference in quality across different devices, and so on. So our solution is called context-aware encoding for Brightcove. It's part of Video Cloud. If you get Video Cloud access, it's available if you're part of the beta by going to upload settings, and then in just profiles, there will be 3 standard profiles which are recommended and which all incorporate dynamic generation of profiles. Now, if you like, you can also create your own manual profile for dynamic profile generator, and if you create manual profile, you could actually explicitly constrain how many encoding points to generate, which frame rates, resolutions to use. By default, we have ladder of about a set of about 20 different resolutions. If you really want to stick only to 720p, 1080p, and something else, you could specify this explicitly. But reality of it, the more resolutions you have, the merrier. The more continuous RD curve you could approximate by picking your points, the more efficient your ladder will be eventually. Now, you could also say what is the minimum quality level, and you have choice of metrics, for example, SSM, PSNR, and such. So, and it's available. This is a brief example of a ladder it generates. So in this case, we picked a sequence that URL is where you could look at full demo. And basically, standard profile uses 8 renditions, and highest rendition is 3.8 megabits. We show that at 1080p it's sufficient to use 2.3 megabits, so it's about 36% savings just at the highest rendition point. But in addition, what is established is that it's sufficient to use just 4 operating points, and moreover, the way those operating points could be placed is that we could actually deliver more bits, more pixels at fewer bits at lower resolution. So you have both a quality advantage at lower bit rates, fewer renditions, less cost of transcoding, and savings in bandwidth. So all wins if content is easy. If content is complex, if it's a rare case, but it happens, well, it's not going to help you that much. And I need to be honest about it. We will still do better accounting to network statistics, and we'll still place rate points appropriately. But if content is very difficult to encode, you will have maybe 8, 10 megabits at 1080p if you need to achieve 1080p. So that's this is it. Thank you. Questions? And if you want to try this product, that's the email where you can send request.
Thanks, Yuriy. How many people were actually able to follow the equations Yuriy had on the slide? Not everybody has a math background, Yuriy.
I worked.
Well, let's switch to hopefully an easier slide deck. Kumar.
There is a slide right there.
Huh?
I think it's in the same text.
It's on the stack?
Yeah, in the same text. Hi. So this is a presentation about content-aware streaming. So what we focus on is streaming optimization as opposed to encoding optimization.
So QBR is a solution that MediaMelon offers. It improves standard adaptive streaming by adding a dimension of information about the content. So as you've heard from the previous two speakers, bitrate and quality are not, they go together in general, but they're not linearly related. So sometimes you increase the bitrate by a certain amount, quality might increase or may hardly increase in certain scenes. And in certain other scenes, increasing the bitrate may bring a substantial improvement in quality. So that's the relationship that we exploit, but we do that for improving streaming, not encoding. And by doing that, we can increase the quality and also at the same time reduce the amount of data used for streaming the video. So the features of QBR is essentially a product. It can be used as a managed service. As I mentioned, it improves quality and reduces the cost of delivery. It works with any existing compression codec, works with H.264, H.265. It can work with any encoder. We sell it as a managed service, but it can also be used as a software product. Works with any player, any video platform. Compatible with, of course, with Dash. We started working with Dash, but also works with HLS and smooth streaming and HTS. And you can use it to optimize each and every streaming session. So when you, when you stream a video to a mobile phone in a congested network versus, to the same phone in a different scenario versus a smart TV, the way you want to stream could be different. And QBR optimizes every session as opposed to optimizing the content while encoding it. The benefits are that, firstly, it will improve the quality of experience. Typically, compression can, ideally will not reduce quality all that much, but reduces file size. But with QBR, it can actually improve quality of experience by delivering the complex scenes at a higher bit rate. So just as an example of this, let's assume that you have a standard bitrate ladder, and when you think about a bitrate ladder, people I think typically select the highest bitrate in a way that is not too high. Otherwise, if the bandwidth is very high, as for instance in a fixed network, the whole video may play at the highest bitrate and take up a lot of your CDN costs. So with QBR, it won't play at the highest bitrate at every instance. It will play at the high rate only when required and pick a lower rate when sufficient. Whereas in a mobile network, let's say the network is not consistent, or you're on a Wi-Fi, you're on your phone and you are going into a lift, and basically your network goes to 0, and the amount of time the video plays before the lift opens again, you're going to have buffering if that's too long, right? So basically, bandwidth is choppy, you're going to have buffering. With QBR, it can actually reduce buffering. It can reduce buffering, it can improve quality of experience by using the available bandwidth more smartly for every session. And it does that while reducing the amount of bits delivered, hence reduces cost of streaming. And also, if you're an operator with limited capacity, it uses that capacity more smartly. The principle is relatively simple. And we have 30 issued patents on this, on the ways to compute quality, communicate that quality information about the video to the player, and improve streaming. So essentially, if you have, in the example here, you have a video encoded into 3 different bit rates: high, medium, and low. With standard ABR, assuming the bandwidth is consistent, it's going to start with a lower bit rate, and then from there on, it's going to play at the highest, at the available bandwidth. So in this case, if it's more than medium and less than high, it's going to play the whole video at that medium level bit rate. Which can be at certain scenes can be high, more than required, and at certain scenes you're wishing that you had more bandwidth. So there are 2 modes on which QBR can work. Broadly speaking, you can it can change it into more than 2 modes. But one of them is reducing the bandwidth, reduces data. So you are saving bandwidth when the scene is not so complicated. The second mode is where you stream certain segments at a higher bit rate, hence improving quality. The way it's implemented, there are a few different ways we can implement this. It works for both VOD and live, so it can characterize video and improve adaptation without latency for live. So this is one of the ways in which this can be implemented. So there is a content analyzer, which is written as a QBR plugin, but it's basically a content analyzer, which can run on an S3 bucket or can be added after the encoder, which characterizes the video. So essentially, it describes the video structure. So how close the various complex scenes are. So the way you would optimize would be different if all the complex scenes are bunched together versus they are far apart. So it considers all those characteristics and creates a metadata file, which then is passed on to the player. And the player's adaptation engine, so it can be any player, that player's adaptation engine can be guided to make better decisions. So it might pick a lower bitrate when sufficient and a higher bitrate when required. It uses the player's bandwidth calculations and helps the player make a better decision throughout. So as I mentioned, this can work with any encoder, any player, no changes in CDN or anything. It can work theoretically with any video platform. And there are different other modes of deploying this. You can do it without anything on the player side. And you can do it purely on the server side and with some pros and cons of the various approaches. So what I'd like to do is to show some results of tests that we did. So here's a video. It's a race car video, which has complex scenes and not so complex scenes put together. So it's this would apply to any sports video, TV show, movies. You have a variety of different complex and simple scenes. This was encoded in 6 different bit rates and 2-second segments, and we played that on a typical network. This is standard ABR. So this one, we played the video in 5 different times. And by the way, this demo is available to anyone. You can send an email to me, and I can share a video link, a URL, and you can play this for yourself, and you can see this working. So we played it 5 different times. The mean MIB was 92.64. The average bandwidth consumed was 2.99. And this is default ABR with that video. With QBR, on the quality mode, what you would see is that the curve here shows normal ABR. Superimposed on that is QBR. You would see that in the simple scenes, lower bit rates were used. In the complex scenes, it went above where what ABR would have picked. So you had an improvement in quality for complex scenes, but at the same time, the amount of data consumed was around 64 compared to 92 with normal ABR. The other mode in which QBR works is a bandwidth savings mode. And in that case, without sacrificing quality, we were able to play the video at around 50 MIBs compared to 92 MIBs. So in conclusion, you would see that we can reduce data by 30 to 45%, as in the case of this video, while at the same time keeping quality consistent or quite likely improving it. And that's essentially what QBR offers. And if you want a link to the demo, you can send an email to me. It's Kumar, Kumar @MediaMelon.com. Thanks.
Okay, thanks, Kumar. Any immediate question? All right, Stefan.
Don't have my presentation on that one.
I don't know if you haven't put it. No. Okay.
Then let's go for that one.
You want to use your own computer as well?
I can either way. I can use this.
You have an HDMI?
Yeah.
All right, okay. Go ahead.
Thanks. Yeah, I promise I will keep it short. So we have different components along the value chain. We have an encoding system, we have a video player suite, and we have a video performance analytics product. So having all those different independent products, I mean, some use just the encoding, some use just the player, some just the analytics. But if you combine that, you have a pretty decent base of metadata out of different processes, which you can use to optimize streaming end-to-end. What we see is that, okay, looking at one part of the value chain is not sufficient. I mean, if you want to really make something happening on the quality side, controlling every component along the value chain, from the encoding to the player to the analytics, gives you a pretty broad range of possibilities. I mean, it would be even better if you can also control the origin and the CDN, where you can extract a lot more data when it comes to routing, which is, for example, done by one of our CDN customers. They combined also here the routing information into the set of metadata. So using this data is quite interesting. I mean, what you can do out of the encoding process. We learned already that video is not static. I mean, you cannot just assume that the video at a bitrate of like 1 megabit has the same quality for the whole duration of the video. I mean, if you have a 2-hour video, you have like black frames at the beginning, you have credits at the end, you have high motion scenes, you have low motion scenes, you have high complexity in scenes and low complexity. So video is a highly dynamic media. So out of the encoding point, you can extract those informations and use, for example, this information, what's the visual quality using structured similarity, PSNR, VMAF, different metrics that suit your purpose, and can decide, okay, what's the quality I actually see in this segment, for example. So on the player side, you have a limited view on the world when you are a player. In the life of the player, you have, for example, the bandwidth you can measure, but the bandwidth is also changing all the time. So in a OTT deployment, one segment, the download bitrate of one segment doesn't necessarily give you any conclusion about the subsequent segment. I mean, the given segment can be watched by another person just a second ago and can be cached in your local organization proxy or, for example, in the edge cache of the CDN. That doesn't need to be the case for the next segment. So you get into a lot of problems there. So also here you need a lot of context information, and you only consider the segment with 1 bitrate that's delivered by the manifest. Dash as well as an HLS manifest has 1 bitrate information for the whole content. You can make it a little bit more granular with a multi-period approach, for example, which is definitely interesting. But at the same time, if you do too much of that, your segment, your manifest file size gets quite large. And last but not least, the analytics information. So what's actually happening on the player side? What's the streamed bitrate? What's the ISP interconnectivity? What's the CDN performance? What's your RTT in the end is valuable as well for the whole end-to-end streaming experience. So having those products, we realized that combining these sets of metadata into a smarter streaming system might make sense. So that's exactly what we did in the per scene adaptation approach, how we call it. I mean, that's per scene. Why we say it's per scene? Because the per title encoding of Netflix gained a lot of interest over the last couple of years, because they were the first ones to decide, okay, 1 bitrate ladder is not the right fit for the variety of content that we have. And animation content has a different bitrate ladder where it's optimal than sports content and action movies, for example. And not only the genre requires different encoding ladders, even different contents, and that was the big step they took. But just defining a different bitrate ladder for the content is not enough. You have to go into the content, into the segments, into the scenes, and that's exactly what we do. We take the encoding information, the scene information, so for every segment we have a second piece of information that identifies the quality in this segment. And based on that, we can make a smarter decision on the player side. In this context, of course, we also use the connection information. We use the connection information of the particular user, what this user had, what type of connection on this IP was available for this particular user in the past. And in the similar region, ISP, AS, for example, was the performance of other users, for example, in the past. Based on that, we can get a pretty good estimation how the bandwidth situation might be for this user. For mobile networks, for example, you can make a bandwidth map where you can, for example, geographically see how the bandwidth situation for a mobile network is at a certain time and in a certain physical location. So imagine you are on the highway, you're driving, your kids are watching a movie, and you are going to a tunnel, for example. With a bandwidth map, you already know, okay, there's a tunnel coming, so I can reduce my bitrate, for example, and stream more segments ahead to have no buffering event while you're out of connection, for example. And last but not least, the buffer fill rate is an important part here on the player side. Measuring bandwidth alone is pretty misleading, as mentioned, as a player. For us, buffer fill state and mapping it to the appropriate quality is the best approach. Where you end up considering buffer, history, connection, and encoding information is basically a linear optimization. Let's keep it simple. For example, you have a backpack. You want to gain the maximum value out of this backpack when you're on a trekking trip. So you think, okay, I can carry 20 kilograms, and what value I want to get out of that? I mean, you can, for example, have a bottle of water that's providing pretty good value to you on a hike. But, for example, 10 bottles of water will not help you because you need some food and maybe a tent or something like that. So the amount of the content, the payload, as well as the value is really dynamic, and really finding the optimal mixture for your hiking trip in the backpack is pretty much the same mathematical problem as finding the right quality and the right streaming configuration for a streaming session. And that's called the Knapsack problem. And that's something you can solve having these different metadata informations to provide a better streaming session on the client. That's one really basic example where you can see, okay, in a standard streaming system, the player and the encoder have no information, okay, is that a complex scene or a simple scene? The quality is changing because you want to maintain a rather constant encoding. So constant bitrate encoding would result, for example, in such a scenario as on the top. You stream the low complexity, simple scene in a rather high quality, and stream the really complex scene in a rather low quality, although they all have 2 megabit. So the user sees a variation in quality across the streaming session. So having a per scene adaptation here reduces the bitrate for the scenes where it's simply not necessary to stream in a higher bitrate because the quality is the same. I mean, it's a simple scene that's pretty easy to encode, so just stream a lower quality. And then when you realize, okay, there's a really complex scene with a lot of motion and with a lot of details, I cannot stream this scene in the same quality with just 2 megabit. I need, for example, 3 megabit for that. Then I can switch up, although my ABR logic would normally not do that. So you can gain a higher quality for those scenes because you saved some bandwidth in your buffer state in the low complexity scene. And that's a pretty good real-life example. So, for example, what you see here, Tears of Steel, you see the first 10 seconds black frames with the title of the movie, the title of the director and the producer, and so on and so forth. So the segments with the black screens with no text at all, I mean, that's not hard to encode. I mean, you can stream those segments with 100 kilobit. I mean, that's a black frame. And in between, you have some text. So, you know, text is not that easy to encode. So to really have a nice quality without ringing around the text, you go up to 8 megabit for that scenario. And then you go into the content. Then, okay, the first scene of Tears of Steel is this rocket launch, which is rather complex with a lot of details. So you go up and you stream the maximum amount of bitrate you can deliver. But there are some scenes in the subsequent part of the movie, for example, where you don't see a significant visual difference. I mean, some recommendations are like 0.3 dB in terms of PSNR, but PSNR is a pretty bad metric to do these decisions. That's something you have to evaluate in the end with subjective tests on larger scales. But here you can, for example, decide, okay, what's the delta that's acceptable for a reduced bandwidth, and then you can switch simply down for those scenes to deliver the same visual quality with a lower bitrate segment, for example. The interesting thing is that we do here is we separate the quality information from the standard dash or HLS segment. That gives you the possibility to be backwards compatible to older systems. And to standard clients. Another benefit here is we heard previously that constant rate factor encoding is pretty much a nice way to guarantee a really good quality. But with constant rate factor, you end up, for example, here in this low bitrate segments for the beginning and high bitrate segments for the complex scenes. That's crashing most of the players out there. So we say, okay, we basically reproduce with that approach a constant bitrate encoding just on the player side. So you have your standard bitrate ladder, which you can do similar to Netflix on a per title encoding basis. And those bitrate ladders are in the way capped and constant bitrate than you can have with a standard adaptive streaming system and your standard adaptive streaming player, the native HLS player on iPhone and so on, play that properly and nicely without problems. But with the additional metadata information, you basically reproduce a constant rate factor or the product of the constant rate factor on your client side, and your player is adapting towards a visual quality information rather than a bitrate information. And that's it from my side. Oh, questions.
Yeah, well, while we're setting this up, yeah.
Sure.
I wonder what kind of metadata you are using to enable this. Is this one of this carriage of timed metadata in MPEG, or you use something else?
Nope, that's proprietary. We could. Hey, we have to earn some money somehow. No, that's basically our additional sidecar file, which is basically an additional metadata file on a per segment basis. We can use, in a really basic approach, you can use, for example, a PSNR value for every segment and for every representation of your dash manifest, for example. But obviously, you go beyond just PSNR. You add, for example, VMAF and structured similarity. But you also provide the metadata file, for example, for your buffer prediction and for your bandwidth prediction as well. So you can end up in multiple sidecar files for that. For the live stream, it's a little bit trickier, but basically what you do is you get out of the encoder the quality information as well. You can do PSNR, structured similarity, and VMAF in real time, and provide in parallel to the dash manifests an updatable metadata manifest as well. In a separate file that's pretty much similarly generated to the manifest. You can do it even dash compliant with a segment list MPD, for example, or with a segment list primarily, yeah, that's the only way. But it's not nice because the segment list approach is not suitable for live, for example, in that case. So we rather go for a separate manifest. It's easier.
So you need a customized
Please
Yes.
go to the question. Let's finish the last presentation, and then we will have some time for questions.
Okay, I will try to be quick. Okay, so to me, Dash and any adaptive streaming methods about creating a framework. In that framework, we can do dynamic adjustment. But when we say we do adjustment, we don't want to do random adjustment or arbitrary adjustment. So this adjustment, to make sense, we have to optimize for something. So I think for our field, the important thing, the things we try to optimize is pretty obvious. Everyone wants to try to optimize quality of experience of the end users and consumers when they watch the video on their TVs, on their cell phones, on their tablets. So what we do here is trying to give you the best tool to do video quality of experience measurement. Okay, if you think about this thing in the whole video delivery chain, I don't want to repeat the whole thing here, but the really point I want to make here is that along the whole video delivery chain, the best way you can imagine to do any quality assessment or quality control is to actually put humans in there. So here, I'm drawing a lot of small humans there. So basically, you want the humans to sit at your head end, sit at your media center, sit in the network, and also sit in the end consumer device to watch the video, to see if all these videos have good quality or not. If you have any problem, any of these guys there report something, okay, there's something wrong about the video, then you identify, okay, this is the exact place you're going to have problem. Of course, this is a very nice solution, but think about this. You have, in a pretty big network, you have thousands of channels, you have millions of consumers watching the video. How many people you have to put in there to do this kind of quality control? So that's something impossible. So all we do at SimWave is simple. Just replace all these humans with automatic software that you can put in there. You can measure the quality. That's exactly what we do. So, so once you have this thing done, then everything else is going to come naturally. You talk about all the optimization. Seems like the whole panel is talking about some kind of optimization. So everything else is coming out of this automatically, right? So you can do all kinds of, you can do quality monitoring, you can do failure recovery, you can optimize streaming, optimize encoding once you have this quality awareness of everywhere in the whole network. Okay, so we know in Dash people have been trying to do something relevant to this. So one thing that people have been trying to do is to, how about we transmit a video quality measure? You can do this measurement at the encoder side, and then you put that into the metadata. You send that to the client side. And we see in the proposal, you see these are the metrics: PSNR, structure similarity, multi-scale structure similarity, VQM, PVQ, and MOS. You can basically embed this information as metadata into the video stream, and then you transmit to the client side. The client side can look at these numbers and make further adjustment. I think that's a good idea. But on the other hand, what I can tell you is these metrics won't work. I hate to say this because some of them are my own babies, so I really hate to say that. But on the other hand, I'm not ashamed of this because structure similarity, multi-scale structure similarity are something I wrote, I authored 13, 14 years ago. So after that, we have done a lot of new developments. So we have something way, way better than structure similarity and multi-scale structure similarity. Okay, so then we talk about what exactly you would need to do this video QoE measurement. So typically people talk about accuracy. That's always the first thing you talk about. But actually, that's not the whole story. You need this to be very accurate. You also need this to be very fast. Otherwise, you won't have something that can really help you to do this monitoring for all the streams you are trying to deliver. And also, you want some other features, and it's very interesting. The audience has, in some earlier time, they have already proposed some question there. So what if the input and output of my transcoder have different spatial resolution? So I have a video 1080 in, I have 330 out. So how I'm going to compare this video? You know PSNR, structure similarity, and VMAP, all these things, you cannot even compute that. How are you going to do that? Okay, so these are one excellent example to have. Right? So there are many other things. So for example, the same video, if you show that video on the TV, or you show that video on your cell phone, you're going to have different experience. Right? But all these metrics, why I say they don't work, because they give you the same quality prediction. You know this is a different quality, different experience, but all these things will give, but I'm displaying the same stream, video stream. Right? So let me give you a very quick, simple example. I'm just playing a video, nothing fancy. Right, so if you look at this video, of course, this video is small. And look at that, that's pretty good quality, right? So most people, when look at that, it's pretty good quality, but actually it has pretty small resolution. The thing is, if you imagine I'm watching that video on my cell phone, I'm holding my cell phone vertical, right? So this is going to be a small portion of my total cell phone screen. I will be pretty happy about the quality of that video. But what if you watch the video like that on the full screen of your cell phone, or even you watch on TV? This is a terrible video. It's very blurry. But now the problem is all these metrics, PSNR, structure similarity, multi-scale structure similarity, VMAP, all these metrics will give you exactly the same number, same quality number. So these things don't make sense. Right? So you really need something that can adapt to device and the resolution. Right? So that's one of the revolutions, the things we have done with Sim+. That's the new metric we talk about. So we designed Sim+, and we are offering these Sim+ to the industry to solve all these problems. Okay, so of course people care about accuracy, and people say, okay, how do you compare with VMAP? Of course, as I said, VMAP, it doesn't have all these properties, the other things I'm talking about. But even if you just talk about accuracy, recently we did a pretty intense test of the video quality metrics, and we actually try to avoid using our own video database, because we do a lot of subjective testing in our lab, and then we do correlation between objective metrics and subjective scores, but that's our own data. So instead of doing that, we use all public databases, right? So in the past 10 to 15 years, the research community, that's the field that I have been working in. So this research community are creating a lot of subject-rated video databases. So what they do is that they collect different videos with different types of distortions, different levels of distortions. They ask humans to score those videos. Then each of the video will be scored by many people, 10, 20, 30, 50. And then they average that, then you have mean opinion score for each of the video in these databases. And these people publish these databases with all the video as well as the subjective scores. Then this is very good for us, because then with the objective metric, you can see your correlation with those subjective scores. And then these are 10 video databases, and then we'll compare our result with other metrics, including here you see PSNR and VMAP. You see Sim+ has the highest correlation with human perception. And the thing is, we use public databases is because you can, actually everyone can reproduce the result. It's not that we claim that we can do that. You can reproduce the result because you have all the data. And meanwhile, if you look at the speed on the right-hand side, you can see that Sim+ is actually more than 10 times faster than VMAP as well. Okay, plus is more the other properties like cross-resolution comparison. Actually, not only that, so for example, even if your video streams, the reference video stream and the test video stream, they're not aligned. One has a few seconds of delay of the other. You can also use Sim+ to compare the quality. So it's a way more advanced method than all the existing quality assessment measure you can find in the industry. And the thing is that all the things I'm claiming here, you can actually talk to some of the audience. They are our users. They already see the effect of Sim+. So if you're interested, just talk to me about Sim+. As I said, let's start from video quality experience measurement. All the optimization stuff is going to come naturally. So you have a best way to measure video quality, then you can do everything else in the right way. OK, so if you are interested in our measure, you can send me an email, or you can talk to me. Thank you.
All right, thanks. OK, I think as the moderator, I have the right to ask the first question. As I understand, everybody is trying to approach this problem from a different dimension. There's the encoding optimization, there's encoding bitrate ladder design, there's metadata, there's streaming client optimization, and then there's the metrics. Well, all these are nice, but I really have a burning question. Now, if there is, let's say I don't have any bandwidth problem in my home network, right? I have a good DSL cable connection, whatever. Here is the question. If my dad is watching something, right? He's an old guy. He doesn't really see very well. I mean, none of your solutions actually will make any difference for him, right? Like, you will still be doing a lot of optimizations, but whereas we could easily send maybe half the bitrate to him, and he would be still quite happy with the quality, right? Now, I understand you want to do optimization per content, and this guy over here, he wants to do, find a way to quantify the quality. I understand, but that's not really personalized. My quality definition is quite different than my dad's and my wife's too. I mean, now she's actually learning from me, so she's becoming more picky as well. But I mean, when we got first married, she wasn't really that picky. So when we are streaming video, this has to be somewhat personalized, in my opinion.
So I can answer that.
I'll take very brief answers just for the sake of time. Please go ahead.
Yeah. So first of all, everyone is actually competing on the bandwidth. So let's at least, the DC level should be that you actually try to make it simple, reduce the issue. ABR can help that. What we are doing can help that. Other technology can help that. But what you're asking is something totally different. That's actually addressed by different workflow where you define priority for the...
But let me ask you this first then. Do you think it's a valid problem? Or I'm just too picky?
I think it doesn't have anything to do with, the quality, because let's assume that I'm watching at home the big screen and my kid is actually watching the iPad. I'm paying the bill. I want to get better video. That should be addressed differently, and there are system and algorithm and solution that actually address that. How
but
to
if
manage
you don't see that well, I mean, why would you still benefit from your kid?
It is very difficult for either a content provider or service provider to actually start replicating and creating a resolution or a profile and streaming per user. However, moving to IP certainly can help that. Having all the resolution and having a control plan that now, based on priority and based on other profile, can actually stream to me higher quality and to my son lower quality. That it's on the top of that. You need first to make sure that you have as less as congestion as possible. But what you're asking is a different workflow that neither of us actually work on that. Different company.
Among the audience, how many people think that that's a valid problem that I was asking? Okay, looks like it's a valid problem.
Sorry, so I
Okay.
think I should give an answer because I'm in the field. I'm exactly in the field. Talking about personal qualitative experience measurement is the thing that we talk a lot in our field when we have academic conferences. We talk about it all the time. So so it's not just about people, older or younger people.
Oh, obviously,
they are different.
Yeah. It was just an example.
So if, for example, so for 3D viewing, like human and man and woman will also be kind of different. So,
Yeah.
but the thing is, this kind of variation, they exist. They are, in some sense, important problem, but we're not at that stage yet. So even for people with the same age, same gender, if you look at, if you test video quality, they give scores, they have some variances. And these issues are relatively small compared with what we can do now. So I'm working on image and video quality assessment. Nothing is going to be perfect. We cannot predict 100% of human perception. Not even the mean opinion score. Mean opinion score. So say even one person and another person, they disagree with each other with certain variances. So if you can predict the mean opinion score, is already a very, very difficult problem. So if you go to that stage, I don't think we're at that stage yet.
So you don't have any solution for me?
So probably we can do something, but this is something that too many things to consider. If you want to put in the product, that's not something you're going to see very soon.
Okay, one quick note. A friend of mine actually did a study, and he says if we can reduce the bitrate when people are not paying attention to the screen, we can save like 50% of the bitrate. Well, that's a lot easier than all of these complex integrals, all that stuff too, right? So, I mean, that's what I'm talking about.
And people are saying if you know people's attention, where video, which location people are looking at.
Yeah, there's a nice lady in a nice dress, right?
Yeah,
women look at the dress and guys look at the ladies.
Yeah.
Yeah, Yuriy?
Yeah, you know, ironically, about 6 years ago at Interdigital, I worked on exactly the same concept. We called it user-aware streaming, where the mobile devices used cameras and other sensors to detect viewer, estimate proximity, use age detection to understand their property, their potential age. And basically, we even had a prototype of the system. I filed a few patents. There are papers. There is even YouTube video of the prototype of this. Well, the reality of it, I think that technology was a little bit premature. It was a little bit too ahead of its time. Maybe sometime later it's going to happen. But market didn't react on this in a promising way.
Okay. Stefan? Say something.
Yes, we see that problem in different scenarios. So, for example, funny enough, VR is a hype, different opinions around that, but it's a good playground for exactly that problem. Because in VR, you see where people are looking at, because the viewpoint is changing. So what we did is, for example, we used the analytics data of the viewpoint and the changing viewpoint together with context information like gender, like age, like IP address and whatever, and feed the machine learning system with that. Then you can estimate personas out of that and viewing patterns of these personas. And different personas look at different parts of a 360-degree movie, and then you can pre-buffer, for example, segments and tiles in these areas, for example. And that's basically where machine learning can further help to use this metadata and approximations towards personas. And you can do similar things with standard video. For example, one thing you see, for example, in Skype and in a lot of other services is awaiting how happy you were with the quality of the current session. And that's something you can give your dad, for example. I mean, if he clicks on it or not, it's the big question. But some people click on those things. And for those people, you can estimate, okay, this person was happy with the current quality. Let's give him a smaller quality the next time, see if this person is still happy.
But then this is actually not that easy. Some people have short-term memory, some people have longer-term memory, right? If something bad happened in the first 5 minutes of the video, some people will just forget about it at the end of the movie, and they will still give a high score, right? So
you can also make it more on a pattern approach, that you say, okay, you have a user, that user is associated with an account. I mean, that's a little bit more for subscription-based services. And based on variations, you only can change one variable. But based on variations on the variables, you can say how the viewing behavior of this person changed, for example. I mean, that's a little bit tricky, and we haven't done too much.
I'm not saying it's easy, it's just...
the VR topic actually is pretty straightforward. That's the surprising thing.
Yeah, but you need to have the HMD device,
exactly.
all that
stuff. What we have seen is that, the viewership patterns are different in different countries that we have seen. So we look at the drop-off curve, how long people see video and when they drop off. And we found, differences in how quality impacts that. In some places, videos in Japan, for instance, videos have so many flashy things, right? All the time. You have news videos, there are like 10 different banners at the same time. There are those kinds of differences we're able to see in data patterns and use that for selecting the right quality to send to users. It will be ideal, looking at Yuriy's idea, to have a camera there and detect, and that'll be the perfect solution in your case. I think it's a good idea. You patented that. That's good.
Well, I actually don't want my content provider to have a camera on top of my TV and see whether I am actually paying attention or not, but yeah.
That feed is anyway streamed.
All right. Any questions from the audience? I want to give the microphone. You start first. You're closer.
Super quick. Thank you. Actually, Ali, this is back to your earlier question on the individually tailored content. To make something like that work, everyone has to have skin in the game, meaning the content of the operator as well as the user. Assuming you have a scenario and you have say your dad, and his eyesight maybe isn't that good, and he's entirely happy with somewhat lower resolution video. You can give him a dial and say, okay, Dad, why don't you turn it down until it still looks good and no worse. But what's his incentive to do that? You have to have something. So you get the video package for a lower rate or that particular content, or get a freebie VOD asset thrown in or something like that. It has to be something in it for him. Otherwise, everyone would crank up the video quality to the far right. I know I would turn it from a scale of 1 to 10. Mine would be at 11, and I'm still shaking my fist at the TV. And it has to be something in it for the operator as well, right? Because otherwise, if everyone cranks it up to 10, what are you going to do? You're going to just deliver highest quality video, even to the people like your poor dad whose eyesight isn't so good. So that's a problem. If we can address that, perhaps there's a way to do individual QoE.
I mean, he bought a 4K TV, but it doesn't see any difference. So.
Yeah. But believe me, I know exactly what you talk about. Yeah, okay. Anyway.
All right, thank you.
Thank you.
Question?
This is completely user preference, right? So we should give a preference for the user so that he can set an option, what quality he wants, and maybe we can give him credit back that you have saved some bandwidth. I share, give him money back with something to his account. Then probably he can choose his setting and you save them bandwidth, and he is also happy with that.
I think a proxy for that is data caps. People are, in many countries you have stringent mobile data caps. So as you get very close to the data cap, you get more sensitive about the data you use. So you can use that as a proxy for what he's saying. So if you want to see some more video before you run out of data cap, you might be able to, put up its.
Yeah, but then you'll tell like, I'm okay, I'll increase my data cap later, but I want to watch the highest quality now. Yeah.
Any other questions, comments?
So for the panel, just want to ask for some advices or suggestions. For any surveillance videos, any good practice on encoding for keep certain quality with as low as possible bitrate?
I think surveillance video storage is at a premium, right? If that is the case, then you can discard higher bitrate scenes when nothing is happening.
Okay. Yeah. Good enough, thanks.
Region-based encoding, region of interest-based encoding is also one thing we see in surveillance. Did you say, okay, every moving part is simply encoded in a higher QP, for example? I mean, that are standard approaches, but yeah.
Going to specifics to what we do, we actually build models, rate quality models for videos as we encode, and naturally we are trying to pick operating regimes that make sense for this particular content. So if video is very easy to encode, we will pick lower bitrate, and we will pick different composition of resolutions that will match the best the properties of this content.
Very specific use case. In this, for example, if you want to monitor, let's say, highway traffic. So part of the picture, you have very high dynamic complexity, and part of that is really just static most of the time. So in this case, they do exist in the same picture. Right.
So what's going to happen is that static regions will be encoded at much lower bitrate, and when there is a moving train, we will bump the bitrate up and encode it at better quality to represent the complexity of content.
Okay. Okay, thanks.
Any other questions for the panelists? All right. Thanks to our panelists. This is the end of our panel.
Thank you.
And now there's a reception outside. Thank you so much.